this lecture includes details about Francis turbine. Francis turbine is always used under medium head application, and it has medium specific speed. It can be radial or mixed flow runner. Okay, as we see from this sketch, the water is coming from through a pipeline from the storage area behind the dam, and then transported to the casing of the turbine, and then radially goes to the runner through the guide vanes, and after gives its energy to the turbine. It converted into mechanical energy, and this mechanical energy is converted into the generator to electrical energy. The water, the water after gives its water energy to the turbine, go away to the downstream through the draft tube. Okay, as we see from this picture, we have here the spiral casing, which takes the water through this valve on the right side of the picture. The valve at the end of the penstock or the pipeline. Then the water through the spiral casing flows through the spiral casing, and then radially goes to the runner at the center of the turbine through the guide vanes. As we see the guide vane here, we have here a ring, a controlling ring that change the opening of the guide vanes. And we have finally the water goes through the draft tube, conical shape tube. Okay, as we see, Francis turbine is developed by American engineer called G.B. Francis. Okay, here also the same sketch. The sketch about Francis turbine. Water is coming through the casing or spiral casing, and then goes radially to the stationary vanes, what we call it stay vanes, and then radially to the guide vanes, and then finally to the runner. And after give its energy to the turbine, it goes through to downstream through the draft. We have here certain Francis turbine used in Europe, or certain power plant in Europe of power output 350 megawatt, working under head 540 meters and discharge about more than 71 meter cube per second. Its diameter 4.8 meter. Outer diameter, and the inner diameter equal 4.3 meter, and the RPM equal 333 RPM. This, as we see from the head, it's applied at high head. As we see, the runner has mostly flow is in radial direction. Then the other one, the other which is used in a certain power plant in Canada, La Grande in Canada, it looks like that we use in a high dam. Its application here, its power output about 170 megawatt, works under head 72 meters and discharge 265 meter cube, and its outer diameter about 6.7 meter, and the height of the blades at the outer, the guide vane itself, height equal 0.4 meter, and the RPM equal more than 100 RPM. This looks like that ours in high dam, and the flow here mostly mixed flow, mix between radial and axial flow. Okay, we have here a sketch for the flow through the penstock and through the turbine and then through the guide vanes. And we have here the head upstream the dam and the downstream the dam, the head difference, we call it overall head H. Here, this sketch, we can see the runner rotating, and we have here outside the runner, we have here the aerofoil section represents the guide vanes, and outside the guide vanes we have stay vanes, which make strengthening, which provide strengthening of the casing, of the spiral casing, to prevent its deflection. Here we have the velocity triangle for the flow through the runner of the guide vanes of the Francis turbine. If that turbine of that runner rotates in clockwise direction, we have the tangential velocity small v in the red color equal pi dn over 60, and we have here v relative velocity of water as it going at the inlet of the turbine runner, we call it vr. The total velocity, we have total absolute velocity will be capital U, which from equation equal v plus vr vectorially. If we resolve this velocity u into two directions, we have the tangential direction capital V, we call it whirl component, and in the radial direction, the pink colored y, we call it flow velocity. At the outlet of the guide of the vane, of the runner vane, we have the relative velocity VR2 takes the direction of its direction is the same as the direction of the blades at outlet, plus V2 tangential velocity at outlet equal omega R2 or pi d2 n over 60. Both the summation of VR2 plus V2 equal U2, the absolute velocity at exit. We also resolved it into two directions. Here we assume it takes the radial direction. This means the radial velocity U2 will be equal to capital U2, and the tangential component here V2 equals 0. Okay. Efficiency drops at in slide 89. We can find that eta hydraulic at part load will be less than at full load due to the existence of a whirl component at exit, and also due to the shocks and the eddies at inlet, and then also when you reduce the load, you reduce the water power, but the mechanical loss power as a kilowatt or megawatt is the same, since it depends only on the speed of turbine. This means that the percentage mechanical loss power will increase in the same time. This means that the part load overall efficiency will be drops significantly as the load drops. Okay. Here from this diagram you can find that we have 4 different turbines: Pelton, Francis, and Kaplan, and tubular turbine. We can find that turbine number 2 represents the efficiency as function of the percentage discharge or the percentage load. We can find that at 100% load, all the turbines have almost the same efficiency. But say if we have the load drops to 40%, you can find that Francis turbine has the lower part load efficiency, lower than Pelton, lower than Kaplan, and tubular. Okay, let us go to the last slide here, effect of head on the Francis turbine runner. We have all these equation, P naught equal W multiplied by Q multiplied by H by efficiency of turbine, and the Q equal K multiplied by d by K due to blade thickness, say less than 1, and Y equal epsilon root 2GH. If we want to design a runner that can work under low head, you have to design it to use a large flow rate. This from the equation of flow rate, in order to increase Q, you have either to increase breadth or to increase Y for the same size D. This means that as you increase B, the size of runner itself will be larger and it will be of mixed flow turbine. The other thing, when you want to increase Y, the internal hydraulic losses will increase as form of exit loss and internal friction loss. This means lower efficiency can be obtained at low head application. This means for low head application you have larger size turbine and lower efficiency. This means all the factors going, you have to go to another turbine. We call it propeller turbine. We have here three shapes of turbine runners. Turbine runners used at from the right to left. From the right we have high head turbine runner or low end turbine runner. As we see, the breadth of the or the height of the vanes at inlet is with respect to the diameter is smaller. In the middle we have a larger breadth, and in the left side we have a larger, maybe larger than the diameter, the mean diameter. This means the first one we have a radial flow. We have in the other tools we have mixed flow runners. As we see from this sketch, we have here efficiency against specific speed for different shapes of turbines. The first turbine is a Pelton wheel. It's about its specific speed about 5 units, and with efficiency about 90%. When you increase the specific speed, this means decrease the applied head efficiency drops. And we are going to the Francis turbine. Francis turbine has efficiency maximum about for specific speed from 20 to 60 about. And then to Kaplan turbine. We have here different shapes, which at 20 you can find the flow radial, and at 80 you can find it is mixed flow. By the way, I have to give a remark to you that when the load decreases, guide vanes should close, and then to reduce the flow to the runner, and at the same time it will reduce the flow through the pipeline that transmit the water from the upstream, the dam, and then to the casing of the turbine. This may cause water hammer, and this water hammer may cause damage either to pipeline or to the power plant itself. You can see this catastrophic accident on YouTube under title Hydropower Plant Accident, or Sayano Shoshaga in Russia power plant station accident. And also have a paper written on this accident. Okay, we can find here which one you could use, Francis Turbine or Pelton wheel, and I will leave this slide to read. Each one of them have its advantage, and you have to take the suitable, most suitable one economically and from the operation. I would like to consider some story in Canada in 80s or in 90s. They have a site, they can use Francis Turbine and Pelton wheel in that site, and the consultation office, after his study, which takes about 1 year, recommend to use a Francis Turbine, and the customer approve that, and the contractor starts to work on the basis of using Francis Turbine other than Pelton wheel due to its advantage over Pelton wheel. Then during the excavation of the site, he faced a problem about the site area, sites. It was very aggressive soil, and also in the salty water. Then they returned back to the consultation office and the customer to return again to Pelton wheel, because Pelton wheel didn't need any excavation. حفر يعني عملية حفر. Then they all different parties agrees to change again to Pelton wheel, and they use it now as Pelton wheel turbine.